Now let us talk about resonance. In simple harmonic motion, if something is set into motion, it is going to oscillate naturally at a frequency that's dependent on characteristics of that material. So, for example, if it was a mass spring system, the time period of its oscillations would be equal to 2 pi square root of m over k. And for a pendulum, it would be t is equal to 2 pi square root of L over g. It's dependent on how long the pendulum is, or how much mass the spring mass system has, how rigid the spring is, how much gravity the pendulum is swinging backwards and forwards in. So things to do with the real system itself. That is the frequency, or that is the time period of its oscillation if it was oscillating naturally. If we wanted to know the natural frequency of this, remembering of course that frequency is 1 over time period, all we have to do is reciprocate the time period as we would have here. And so the natural frequency of a spring mass system would be equal to 1 over 2 pi square root of k over n. And for a pendulum, it would be 1 over 2 pi square root of g over L. Every object would have a natural frequency dependent on the actual dimensions and stiffness and the actual physical properties of the system. Now, of course, we could add some oscillations. We could add energy at a particular driving frequency. Now, if we added energy at a rate that was different to the natural frequency of the object of the system, then we find that it wouldn't, sometimes we would be pushing against the pendulum as it was moving towards us. It would kind of cancel out. It wouldn't always add. But if we pushed the pendulum as it was moving away from us, and we did that every time it was moving away from us, clearly the amplitude is going to build, like pushing somebody on a swing. If the driving frequency matches the natural frequency of that object, then what we find is the amplitude starts to grow. Here, a graph of the amplitude, a peak, where the frequency is equal to the natural frequency. So in the Tacoma Narrows Bridge disaster, which killed a small dog, what happened was the driving frequency provided by the wind matched the resonant frequency of the bridge, and what started out as just some flutter turned into an oscillation that's amplitude got larger and larger until the bridge fell down. Now it makes you wonder what could have been done to stop that from happening. Well, let's have a little bit of an exploration. So if we're quite happy that the natural frequency is equal to 1 over 2 pi multiplied by square root of k over m, and we're also happy that the angular frequency is equal to 2 pi f, then we can actually express the natural angular frequency as just equaling square root of k over m, because the 2 pi has disappeared into the omega. So if no damping occurs, that is the resonant frequency. And so for a particular bridge, you could model what k and m might be, and then you could work out in advance what the angular frequency for its natural frequency, the natural angular frequency, what that's going to be. But one thing that does change the game as to the angular frequency that causes resonance is if there is damping. If you are systematically taking energy out of the system, then it affects how the energy can build in the system when the driving frequency is equal to the natural frequency. Whereas if there's no damping at all, the natural angular frequency is square root of k over m. If there is damping, it's modified by subtracting from this a ratio of b squared over 2m squared. So first of all, mass appears in it again, and that's quite obvious. But b, remember that b was the damping coefficient that we saw in the damping chapter. It's equal to force is equal to negative b multiplied by velocity. So force divided by velocity would equal essentially this coefficient. And so what it really represents is the amount of damping that is going on here. And so if this second expression, minus b squared over 2m squared, you can interpret that as the reduction in the squared resonant frequency due to damping. So what has happened to the frequency? Well, it has been reduced by the presence of damping. So when b is equal to 0, the term disappears and it's just straightforward square root of k over m. But if b is bigger than 0 and the damping coefficient is a real number and the damping is happening, then the damping reduces the resonant frequency below the natural frequency. So by applying damping to a resonant system, I can shift the frequency that it resonates at, the natural frequency. So I can do basically two things to my system. I can physically change its characteristics, adding mass or increasing its stiffness. Or alternatively, I can apply damping to it. If I apply damping to it, it actually changes where the peak is, so that if I was finding accidentally that environmental conditions was causing a driving frequency equal to the resonant frequency, I can physically shift where in frequency space the natural frequency of the bridges to avoid that particular wind speed causing an out of control growing oscillation on my bridge. Now, the most common question you're going to be asked is just for examples. So it's really useful to understand why these are resonance examples, musical instruments. So go back and take a look at those standing waves forming on a guitar string, when you can fit in half a wavelength across the length of the string, or you could have 2 nodes or 3 nodes. An important thing here to realize is that if you can fit multiple different size waves on the same string, the different harmonics of the guitar string, it's important to realize that in real systems, the natural frequency of oscillation, it could represent the first harmonic of that system, but that all of these systems are they're gonna have more harmonics, and their harmonics are gonna get closer together as you go into higher frequencies. What you might find is that the biggest impact would occur if your driving frequency matches the fundamental frequency, the first harmonic of your system, but that you would actually have secondary peaks where if your driving frequency matched the natural frequency of, say, the second harmonic, again, that would be a resonant frequency. And so it may not be as simple as just having one peak on the graph. There might be multiple peaks. Anything that involves standing waves, reflecting a wave back on itself, so that you've got this build-up of the amplitude in certain places, like the constructive interferences on the wave where it is an antinode and it's got really big. What is used in a microwave oven when the microwaves are sent around and then they add on themselves and they create these regions where the amplitude of the microwave is really large and it causes the water molecule to vibrate in those places. This is an example of resonance. Now, radio and TV tuners, how do you tune into a certain channel? Well, you need to make sure that your TV is sensitive to the radio waves that are coming in, and so you get your TV to resonate at the same frequency as the wavelets come in. You essentially change your aerial's natural frequency until basically it matches what the driving frequency of the incoming communications is, and so then you get an amplification of that signal over other signals. Bridges and buildings, sometimes they're designed to move along with certain conditions. Like earthquakes are actually designed to move, deliberately to move. Those resonances are a useful thing in the building. If it was rigid and it didn't move, the whole building might fall down. MRI scanners, nuclear magnetic resonance. That's a story for another day. Destructive examples of resonance: the Tacoma Narrows Bridge collapse. You're not an engineer unless you've watched that video. The Millennium Bridge swaying side to side. Soldiers marching in step, causing bridge vibrations. Aircraft wing flutter, leading to structural failure. So they have to make sure that your wings don't fall off. And of course, tall buildings swaying dangerously in strong winds. We have to just make sure we cancel out any kind of movements whose amplitudes are getting larger and larger. So this important detail that damping actually lowers the resonance. Of course, damping is taking energy out of the system, and resonance is actually energy growing in the system. So to start with, it seems straightforward that taking the energy out is going to counteract putting energy in, but it's a little bit more nuanced than that. So the two things: first of all, damping actually changes the natural frequency of vibration of the object just slightly. And also, and here's the very thing, as the natural frequency of the system is approached, the amplitude of the oscillation becomes greater. But it says if the system is lightly damped, there will be a sharp resonant peak. But a heavily damped system will have a much broad and low resonant peak. So what happens if a heavily damped system, actually it will not respond necessarily just to one frequency of driving frequency, but it actually becomes susceptible to a broader range of driving frequencies, but the effect is not as exaggerated. The peak is not so high as in a lightly damped or undamped system.